In the silence after a star dies, a city-sized core awakens spinning hundreds of times each second, wrapped in magnetic fields strong enough to bend light. It ticks like a cosmic clock, then stutters with glitches, cracks its crust and unleashes storms of X-rays and gamma rays. Its winds inflate glowing nebulae. Its collisions forge gold and paint the sky with kilonova light. From the crust's nuclear pasta to a core that may melt into quarks, every beat raises a deeper question. Neutron stars, the universe's densest cosmic engines. In the beginning, clouds of cold gas gather under gravity and thin filaments braid through the dark like unseen rivers, and inside those strands turbulence knots matter until pockets grow dense enough to collapse. In star-forming regions imaged by the Hubble Space Telescope and the James Webb Space Telescope pillars and shells hint at how newborn suns push on their cradles. But among the many modest stars, a small fraction draw in so much material that their cores become furnaces of uncommon intensity. These massive stars live quickly burning hydrogen to helium, then helium to carbon and oxygen step by step, up a ladder of fusion that adds weight to the core while the outer layers surge and churn. The European Southern Observatory documents such giants in nearby galaxies, and in the Milky Way's spiral arms, where their light sculpts glowing nebulae and their winds carve cavities that will later witness collapse. The lives of these behemoths are not gentle. Their cores, pressed by gravity and heated by fusion, must balance outward pressure against inward pull, and for a while equilibrium holds. Yet the heavier the core becomes, the more precarious the balance. When fusion reaches iron, a nucleus that cannot release energy, by being fused the central engine stalls. In that silence, neutrinos flood out, pressure plummets, and the star's inner layers rush inward. In a moment that telescopes like Chandra and XMM Newton can only study after the fact, an implosion flips into an explosion, and a shock wave hurls the outer layers back into space. What remains at the center depends on the core's mass and the violence of the blast. If the core is heavy enough to crush beyond even neutron pressure, a black hole may form, but for a wide band of progenitors, gravity first squeezes electrons into protons, birthing neutrons, and a gas of neutrinos that carry away a torrent of energy, and what is left is a star made of neutrons, small, fierce, and so dense that a teaspoon would weigh as much as a mountain. The path to such an object is written in the spectrum of a supernova's fading light, in the ringed debris expanding for centuries, and in the sudden appearance of a fast radio and X-ray source where no pulsation had been seen. Space agencies and observatories catalogue the remnants, comparing shells mapped by radio telescopes such as Meerkat and the Very Large Array, with compact sources seen in X-rays by Chandra and in gamma rays by Fermi. The Crab Nebula, born from a supernova recorded 1,000 years ago, is a classroom where a pulsar's wind inflates a luminous bubble and ripples drift outward like the wake of an invisible oar. That engine is a neutron star, and even at this earliest chapter the story bends toward extremes. Gravity concentrated into a sphere about the size of a city, magnetic fields twisted into coils, strong enough to guide charged particles at nearly the speed of light, and rotation rates measured in fractions of a second. The term pulsar will come later in this narrative, defined as a rotating neutron star whose beams sweep past Earth like a lighthouse, and with it a way to measure time in the wild. For now, the emphasis stays on origins, because the birth of a neutron star imprints the properties that later instruments will measure. The spin rate is set by the angular momentum of the collapsing core, so a slow ancestral twirl becomes a frantic whirl as the radius shrinks by orders of magnitude, and the magnetic field is amplified both by compression and by dynamos that operate while the hot newborn star is still convecting. The exact outcome depends on subtle physics that astronomers strive to read from light and from gravitational waves. When LIGO and Virgo listen for the tremor of a core collapse, they are chasing a signature that could reveal asymmetries hidden inside the blast. When NICER perched on the International Space Station times X-ray pulses from neutron stars, it infers the compactness that traces back to the equation of state, the relationship between pressure and density in matter, pushed beyond nuclear norms. The factories that seed neutron stars also mint the heavy elements. In some cases, the explosion itself forges new nuclei, and in other cases the newborn star later merges with a companion of its own kind, launching a kilonova that pours out gold and platinum and a spectrum lit by radioactive decay. The rich chemistry that astronomers see in ancient stars hints at multiple pathways, and the ratio of elements whispers about how many massive stars die in isolation compared to those that meet a partner in a final dance. The foundations of the neutron star story therefore stretch from stellar nurseries to chemical fossils in the galactic halo, and every data point adds weight to a simple arc. The universe builds complexity through violent transitions, and among the most consequential of those is the birth of a neutron star. Telescopes do not watch the instant of birth directly very often, but they read the room after the event. Shock-heated gas emits X-rays. Dust glows in the infrared. Filaments expand at measurable speeds, and proper motion maps drawn over years by the Hubble Space Telescope show knots flying outward while the central compact object kicked by an asymmetric blast sprints through space. Instruments like Green Bank and Parkes rake the sky for new radio pulses, hand in hand with the Chinese 500-meter aperture spherical telescope that reaches deeper toward faint and distant beacons. Each discovery feeds back into models of stellar evolution. How fast must a star rotate before collapse to yield the fastest pulsars? How strong must the natal magnetic field be to become a magnetar? How often does fullback gas surround the newborn star and bury its field under a temporary shroud? These questions are not abstractions. They are levers, and small shifts change the later behavior that observers will measure. Seen this way, the birth scene is not a curtain that falls and then rises on a new act. It is a continuous process because expansion interacts with the surrounding medium, and the compact star keeps cooling, shedding neutrinos, and settling its crust and core over thousands of years. The crust first freezes, then ages under stress. The interior becomes superfluid, a quantum state where vortices hold angular momentum like tiny gears. Even those later specifics have roots in the first minutes when temperature profiles and composition gradients set the stage for future adjustments. The result is that every neutron star carries a memory of its origin, and that memory is legible in spin field motion and environment. The science agencies and collaborations that survey the sky are building a living atlas of these memories. The European Space Agency's Gaia mission maps stellar motions linking runaway neutron stars to their birthplaces. The Atacama Large Millimeter Array images dust and molecules stirred by the blast. The Very Large Telescope studies the faint counterparts of central compact objects that do not pulse, suggesting a spectrum of outcomes beyond the classic lighthouse. The picture that emerges is not static but evolving. It says that neutron stars are not rare curiosities but an expected phase for many massive stars, and that the universe continually rolls them off the line in clusters and associations where massive siblings are born together. It says that where a supernova shell glows, a small hard gem may be hidden within, and if a beam happens to cross our line of sight, a clock will announce itself against the noise of the galaxy. This is the ground from which later mysteries grow a star that lived fast-forged heavy elements, and then when its options ran out, collapsed to a density that changes the rules for matter and for magnetism, leaving behind an engine that will test instruments, timing methods and theories for decades to come. The collapse to a core begins as a quiet failure of pressure, a retreat that starts deep in the crowded heart where particles jostle and bind, and then the loss of support widens until an entire star must yield. A massive star has lived fast, building an onion of elements by fusing lighter nuclei into heavier ones, while gravity presses inward without rest. At last, the central region becomes iron, a nucleus that does not return energy when fused, and the engine that once pushed outward goes dim. Electrons are driven into protons, turning them into neutrons, while a tide of neutrinos carries energy away, and the temperature and density climb beyond the comfort of matter as it is usually known. With electron pressure gone, the core accelerates inward. At unimaginable compression, nuclear forces resist further squeezing, the infall halts, and the inner core rebounds. A shock wave forms at the boundary and rushes outward through layers that are still falling in. For a brief time it looks as if this shock may die as it loses energy, breaking nuclei apart. Then neutrinos born in furious numbers deposit heat in a region just behind the shock, and the front revives. The entire outer star responds as if a trapdoor has opened beneath it. Layers that were drifting inward are struck by a wall of energy and momentum that races past, reverses their motion, and hurls them into space. The explosive debut is recorded later in the speed of expanding debris, in the ruffled shapes of filaments and rings, and in the chemistry of newly forged elements that seed future stars and planets. What remains at the very center is a hot, compact object, only a few tens of kilometers wide, a proto-neutron star that glows not with ordinary light but with an ocean of neutrinos streaming out. During the first seconds, cooling is so intense that the internal structure changes in real time. The outer layers begin to crystallize into an extraordinary crust, whose nuclei are squeezed into rods and sheets, sometimes described as nuclear pasta, a geometry pressed into being by gravity that forces matter to compromise between attraction and repulsion. Deeper within, neutrons pair and slide past one another without friction, forming a superfluid. This transformation sets the long future. Superfluid vortices arrange themselves like tiny threads that hold angular momentum, and their later pinning and unpinning will explain sudden spin-ups called glitches. The overall spin is inherited from the collapsing core. What had been a slow rotation in a sphere of millions of kilometers is now condensed into a city-sized object, so the spin quickens into many turns each second. Magnetic fields that once threaded a swollen star are forced into a smaller volume and grow far stronger, and dynamos driven by early convection may amplify them further. Whether the final field is merely strong or utterly overwhelming, it is patterned by birth conditions that push some remnant stars toward the magnetar state, where magnetic tension stores energy like a bent bow. The explosion is rarely symmetric. Instabilities ripple through the hot matter behind the shock as neutrino heating and rising bubbles shove in uneven ways. Dense knots in the falling material resist more than their surroundings. These asymmetries give the newly born star a kick. A single compact object may be launched at hundreds of kilometers each second, and later observations find such remnants displaced from the geometric center of their shells and racing through the galaxy on long, lonely tracks. Fallback may alter the outcome. If part of the ejected mantle lacks the energy to escape, it can rain back onto the proto-neutron star minutes to hours after the blast. That returning material can bury magnetic fields beneath the surface to drift back out over centuries. In extreme cases, enough mass may fall back to push the star over the threshold, where even neutron pressure cannot hold, and the core collapses again, this time into a black hole. In many other cases, the mass stays below that boundary, and the object hardens as a lasting neutron star. The environment that surrounds the survivor is also shaped at birth. The shock bubbles the envelope into rings, and arcs and jets may be carved where rotation and magnetic fields channel energy. In some directions the blast rushes nearly unhindered and opens cavities, and in others it thumps into dense clumps and leaves behind bright knots. Over time the expanding shell cools, sweeps up gas and dims, yet the central engine can keep working. A wind of particles streamed from the magnetic poles, or from the outer magnetosphere inflates a bubble inside the remnant, a pulsar wind nebula, where electrons spiral in magnetic fields and paint the space with radio and X-ray light. The first days to years after birth continue to write the ledger that astronomers will later read. As cooling proceeds, the crust settles and cracks as it shrinks, and these small quakes foreshadow the larger seismic events that magnetars will one day produce. The magnetic field diffuses and rearranges, dragging and stressing the crust. The superfluid in the inner regions locks to the crust in complicated ways through pinning to tiny imperfections, and the difference between the rotation of the superfluid and the solid lattice builds slowly a strain that waits for an opportunity to release. Even the light that leaks out carries a signature of this origin story. Thermal emission from the surface in the early years reveals hotspots that could be glowing polar caps, while non-thermal light from charged particles accelerated along open field lines shows how the magnetosphere is configured. Where the line of sight happens to cross the beam, pulses begin to arrive at Earth like the sweep of a lighthouse, and the newborn engine declares itself as a clock in the dark. The clock is not perfect, and that imperfection is a gift because it points inward. Tiny slowings trace the loss of rotational energy to radiation and winds. Sudden jumps trace internal transfers of angular momentum. Changes in pulse shape hint that the magnetic architecture is not rigid, but can rearrange like a weather system. Later in this narrative, such behavior will serve as clues to interior states that cannot be sampled directly. In the first act, these clues are minted. The collapse to a core therefore stands as both an ending and a beginning. It ends a star's effort to hold gravity off by fusion. It begins an engine that runs on stored spin and stored magnetic energy, an engine that compresses matter into a state where new rules rise. The universe rarely grants a direct view of the pivot, but across many remnants the pattern repeats with variations that refine the story. Some remnants are quiet and show no pulses, perhaps because geometry hides their beams, or because their magnetospheres never set up the conditions for radio emission. Some blaze with gamma-ray flares when magnetic tension overcomes the crust. Some spin so fast that a millisecond can contain an entire turn. All carry the stamp of that first failure of pressure, the rebound, the revival of the shock, the kick, and the slow settling that follows. From that stamp, the later science flows timing, mapping, weighing, and the pursuit of equations that describe what matter becomes when even atoms cannot endure and only the core remains. Across the Milky Way, neutron stars dot the spiral arms like iron seeds left by vanished giants, and the effort to count them becomes a lesson in how the galaxy hides its most extreme objects in plain sight. Radio telescopes rake the sky first, because the beams from rotating neutron stars, the pulsars, cut space with reliable rhythm when the geometry lines up with Earth. The park's multi-beam survey transformed the census by widening the search lanes, and the Greenbank telescope and the legacy of the Arecibo Observatory added depth with exquisite sensitivity, while Meerkat in the south and the 500-meter aperture spherical telescope in the north open paths to fainter and more distant targets. In these surveys, pulses arrive later at lower radio frequencies because the interstellar medium delays them a dispersive effect that turns each detection into a yardstick called dispersion measure, a measure that roughly tracks the total electrons along the line of sight. From these delays, astronomers infer distances and trace where pulsars cluster. They gather near the plane where starbirth is common, but their numbers thin with height above the disk in a way that reflects the kicks they received at birth. Some sprint on orbits that carry them thousands of light years from their birth clouds, leaving the shell behind and crossing empty lanes between spiral arms. This motion complicates any map, and the map was already incomplete because the pulsar beams are narrow. Only a fraction of neutron stars aim at Earth, a beaming fraction that grows smaller for slower rotators, so every detection hints at many hidden siblings that never sweep across the planet. There are more veils. In the inner galaxy, interstellar gas scatters radio waves into a haze that smears out pulses, and the most crowded regions show dramatic absorption that darkens sightlines. To reach into those zones, the Fermi Gamma Ray Space Telescope has catalogued pulsars that shine in high-energy light, including many that are radio-quiet or radio-faint at Earth. In X-rays, Chandra and XMM Newton uncover young pulsars embedded in shells, and pulsar wind nebulae, and they reveal central compact objects that show hot surfaces, but no detectable pulses are classed that hints at magnetic fields, twisted or buried by fallback. A separate group, the isolated thermally emitting neutron stars nicknamed the Magnificent Seven, glow softly in X-rays within a few hundred parsecs, and demonstrate that some neutron stars live quiet, unassuming lives as cooling embers. The coexistence of these populations forces models to bend. If neutron star births distribute spin and field too narrowly, the observed diversity makes no sense. If kicks are too strong, stars fly far above the plane, and the observed scale height would run high. If kicks are too weak, the observed spread would collapse. Every new detection sharpens the picture and moves the acceptable parameters, yet patterns still refuse to sit perfectly still. In the deepest searches, astronomers find long-period pulsars whose beams turn slowly challenging ideas about what magnetospheres will allow. Giant pulse emitters erupt with rare, stupendously bright flashes that outshine their own average behavior and point to conditions in the magnetosphere not captured by simple models. Timing campaigns uncover young pulsars that alternate between distinct emission modes and sometimes fall completely silent, then return without warning. These puzzles suggest a magnetosphere that can reorganize on its own, like a weather system under unseen forcing. In clusters of ancient stars, millisecond pulsars gather in surprising numbers. These are neutron stars spun up by accretion from companions, so the crushing of a dense core and the companionship of a donor star must both be present. The abundance in globular clusters implies that close encounters between stars are common in those crowded environments, and the final products then serve as arrays of clocks to probe the gravity fields in their neighborhoods. Outside clusters, many millisecond pulsars live in binaries, where their winds have stripped companions down to planetary husks or tenuous clouds, and these spider systems produce eclipses and timing quirks that reveal winds in combat. The distribution of magnetic fields across populations also wanders from expectations. A subset of pulsars powered by rotation emit in gamma rays with luminosities that push simple efficiency limits, as if some channels tap spin energy with unexpected success. Magnetars huddle at the high field end with periods of several seconds, and show bursts and giant flares that challenge ideas about how crusts fracture and reconnect. A small set of central compact objects exhibit very low external fields, combined with hot surfaces implying either fields buried under the crust or internal heat sources that keep them glowing. Putting these groups together feels like assembling a family portrait from relatives who never sit for the same picture. Even the birth rate is slippery. Counting young pulsars near supernova remnants suggests one flow, while extrapolating from radio surveys with beaming corrections yields another, and gravitational wave detections of merging neutron star binaries imply yet a third history over millions of years. The rate must reconcile with the chemistry of the galaxy, because neutron star mergers create heavy elements that appear in the atmospheres of old stars, and the distribution of those elements with age says that not all heavy element factories wait for long delays. That points back to some contributions from core collapse explosions themselves, a mixture whose proportions remain under debate. Instruments that do not see pulses still help with the census. The Gaia mission maps the motions of stars, and its identification of runaway stars and disrupted binaries refines models of natal kicks by showing which systems were broken by a supernova. The Hubble Space Telescope tracks moving knots in supernova remnants and sometimes sees the compact object walking through space, adding a direct vector to the record. The Atacama Large Millimeter Array images cold gas and shows how shock fronts chew through clouds, leaving cavities where a pulsar wind nebula breathes. These environmental clues act as both context and calibration. Even with this expanding atlas, selection effects loom at every turn. Searches favour certain periods, certain pulse widths, and certain positions on the sky, where the observation schedule is kind. Radio observations favour beams that are bright at their chosen frequency. Gamma-ray searches favour objects with large spin-down power. X-ray telescopes stare in narrow fields for valuable time and often target known remnants. This reality means that each new instrument and algorithm can tilt the census and shake a previously comfortable conclusion. Artificial intelligence now combs through archives for pulses hidden by noise or missed by earlier filters, and new low-frequency arrays peel back the veil of scattering by seeing coherent patterns in the haze. As the census grows, so does the network of clocks that time keeps for the galaxy. Precision timing arrays stitch together many millisecond pulses to listen for slow ripples in space-time from supermassive black hole binaries, and their first hints of a background hum confirm that even distant giants can influence these small dense stars that serve as metronomes. Counting neutron stars therefore becomes more than a tally. It becomes an organizing backbone for a set of experiments that reach from the outer magnetosphere to the behavior of matter under crushing pressure. The mismatches between prediction and observation are not failures. They're invitations to open the interior and redraw the distribution of spin field mass and temperature at birth. Each catalogue release writes a new column of questions. Where are the missing slow pulsars that should have been born with moderate fields? Why do some central compact objects hide their pulses so well? How many beams never cross Earth because their magnetic and spin axes favour the empty sky? The unanswered parts keep the narrative alive. A galaxy of remnants is not just a map. It is a moving, uneven record of stars that failed in the right way, that turned collapse into a new kind of engine, that now populates spiral arms and halo and clusters with silent heat, or with beams that sweep the darkness, and that collectively demand models elastic enough to accept surprise without breaking. A rotating neutron star declares itself as a clock in the dark, and the act of turning those pulses into time becomes a discipline where patience is power and small errors peel away to reveal the interior. A beam tied to the magnetic poles sweeps the sky with every spin, and when the line of sight intersects that beam, the pulses arrive with metronomic regularity that rivals the best laboratory oscillators. Yet the very deviations from perfection are the messages worth reading. Observers collect arrival times across many frequencies because the interstellar medium delays low-frequency waves more than high-frequency waves, a dispersive fog that turns each detection into a measure of the electrons along the path. By solving for the dispersion measure, they lift the veil of plasma and recover the intrinsic beat. Then they translate observatory clocks to an inertial frame by correcting for Earth's motion around the Sun and for the slow sway of our planet in space, so the reference becomes the solar system barycenter, where gravity sums to a common anchor. In this cleaned frame, the pattern of arrival is compared to a mathematical timing model that accounts for the spin period and its slow loss to radiation. And when the star belongs to a binary, the shrinking and stretching of intervals as the companion's gravity tugs the orbit are encoded too. What begins as a series of flashes becomes a set of parameters that trace real forces. The remarkable stability of millisecond pulsars turns this practice into precision metrology. Spin periods of a few thousandths of a second inherited and then polished by past accretion create pulses that can be averaged into a sharp template to which individual arrivals are aligned. Profile stability is never perfect, but for many sources it holds well enough that deviations at the level of microseconds can be measured over years. In those deviations hide signatures of gravitational waves passing between us and the pulsar and pulsar timing arrays knit many millisecond pulses into a galaxy-sized detector for slow ripples of spacetime from supermassive black hole pairs. The first broad hints of a nanohertz background turned up as a common red noise with a distinct spatial pattern across arrays on multiple continents, a discovery that confirmed a long-predicted chorus humming through the Milky Way. That same sensitivity presses on other fronts. In a relativistic binary light that grazes the companion, experiences a delay called the Shapiro effect, and the shape of that delay maps the geometry and the mass of the companion to high precision. The periastron of an eccentric orbit advances by a small angle, each cycle under general relativity, and the advance is measurable in a handful of systems tying mass and inclination together, and sometimes proving that the unseen partner is itself a neutron star. The heavy hitters of the field, including the Neutron Star Interior Composition Explorer, mounted on the International Space Station link timing, with pulses seen in X-rays, so that radius and compactness can be teased from subtle energy-dependent shifts as the surface rotates under hotspots. Even without a companion, timing is alive. Young pulsars exhibit timing noise, a wandering of their rotation that looks like a random walk and may originate in magnetospheric torque changes or in internal superfluid dynamics. They also glitch sudden spin-ups that step the period to a slightly faster value and often relax over days to months. The prevailing picture frames glitches as unpinning events in which superfluid vortices that were anchored to the crust let go, transferring locked angular momentum to the lattice in a rush. The sizes and waiting times of glitches form distributions that differ from star to star, implying an interior with local rules set by temperature, crustal impurities, and magnetic stresses. Some pulsars show quasi-periodic timing noise that hints at cycles of magnetospheric state changes echoing the mode switches seen in pulse shape and brightness. Others show long-term breaking index values that do not match the simple expectation for a rotating dipole, implying that the torque evolves as currents and field configurations drift. All these features turn clocks into seismographs for matter we cannot touch. The medium between stars bends the record also, and timing must confront that moving veil. The dispersion measure is not constant. It changes as clouds drift across the line of sight and as the solar wind breathes with the seasons and the cycle of the sun. Multi-frequency campaigns chase these changes, modeling the chromatic delays, so that the white timing residuals can settle near the thermal limits of the radio receivers. Scattering by small-scale density irregularities broadens pulses and adds a tail that varies with both frequency and time, a trait that low-frequency arrays used to study the turbulence of the interstellar medium, while high-frequency observations leap over the haze. When timing reaches into the microsecond regime, the observatory and the time standard become part of the experiment, and so long baselines use redundant clocks, transfer techniques and comparisons across facilities to pin the time to an absolute scale. The reward is a stream of tests of gravitational theory and a portrait of the engine behind the pulses. In one famous binary of two neutron stars, the orbital period decays in exact agreement with energy loss to gravitational waves, a direct reading of general relativity in a regime far beyond the solar system. In another, the Shapiro delay maps the mass of a white dwarf companion with such precision that the mass of the pulsar can be nailed down to values that challenge the stiffness of the equation of state, forcing nuclear physicists to decide how matter resists compression at densities several times that of an atomic nucleus. The science agencies spread the effort across wavelengths. X-ray timing follows hotspots that drift as magnetic fields rearrange. Gamma-ray timing extends the reach to pulsars too faint for current radio instruments. Optical timing in rare cases watches a companion brighten and dim as it is heated by the pulsar wind folding photometry on the orbital clock to recover geometry. Each band brings a lever, and together they pry open uncertainties one notch at a time. Yet the deeper the timing goes, the less comfortable pure certainty becomes. Pulse profiles that once looked stable show minute shape, changes that bias arrival times if not modelled. Dispersion measure fluctuations masquerade as red noise, and can be confused with the gentle signature of a gravitational wave background if not separated with care. Glitches reset the phase count and demand robust cross-checks so that cycles are not lost when the star jumps. Even the beam itself may drift on timescales of years as the magnetic axis precesses or as currents redraw the architecture, shifting the arrival of the centroid of the light. These challenges are not failures, but the living complexity of an engine that is at once regular and restless. The craft answers by refining templates using wide bandwidth receivers to capture chromatic behavior in one shot, combining arrays to overlap sky coverage, and building datasets that span decades so that slow processes can be disentangled from fast ones. A single clock in the dark is a marvel. 1,000 clocks spread across the sky become a woven instrument that hears whispers from the core and from the cosmos beyond, and as timing improves, the small deviations that once looked like nuisances turn into the very reasons to believe the inference. The pulse is steady enough to follow and unstable enough to inform. It is a paradox that keeps the work honest. A neutron star turns space around it into a magnetic machine, and the magnetosphere that rises from the surface to the distance where co-rotation would demand the speed of light is both an engine and a stage where storms and funnels sculpt beams and winds. The magnetic axis usually tilts away from the spin axis, so as the star turns, the field sweeps like a rigid structure at low altitude and then strains near the light cylinder where co-rotation cannot be maintained. Near the surface, footpoints of open field lines gather at the magnetic poles to make polar caps, and from these caps charged particles are pulled into narrow funnels that climb outward along lines that never close back on the star. The rest of the field closes in loops that corral plasma and guide currents back a two-zone architecture joined by a thin current sheet that wraps around the star and flutters beyond the light cylinder, where magnetic stripes of opposite polarity collide, In this landscape, electric fields parallel to the magnetic field arise where the supply of charge cannot meet the demand set by rotation, and in those gaps particles are whipped to energies so high that they radiate hard photons by curvature as they are forced to follow bent field lines. Those photons strike the magnetic field and split into matter and antimatter, a pair cascade that fills the magnetosphere with the dense streaming plasma. Once enough pairs are created, the plasma can screen the accelerating fields and steer the system toward a state close to force-free, where fields carry energy outward and the matter tags along as a light tracer. But this near balance never fully settles. Tiny deficits and rearrangements make room for fresh acceleration, so the engine alternates between quiet flow and bursts of raw push. Radiation fingerprints this dance. Curvature radiation in the high-altitude gaps lights the sky in gamma rays with pulse peaks that often lead or lag the radio peaks, a geometry that says the sites of radio and gamma rays are not the same. Synchrotron radiation paints the inner nebulae with broad bands of X-rays and optical light, as particles spiral in magnetic fields, either just outside the light cylinder or in the wind zone where stripes reconnect. Inverse Compton scattering lifts softer photons to higher energies in rare cases where dense fields of light, perhaps from a companion or a nebula, cross the particle streams. In radio, the story is stranger. The coherent radiation demands that charges move in step, and theories invoke plasma instabilities, bunching and maester-like growth under magnetic guidance. Yet no single model captures all observed habits at once. Polarization swings trace the magnetic geometry as the beam sweeps across the line of sight, and sudden orthogonal jumps suggest that more than one polarization mode can dominate in rapid alternation. Circular polarization appears and fades across the pulse window as if the beam grazes different layers of plasma, with different magneto-ionic properties. Subpulses drift in organized bands that march through the window, with a rhythm that implies rotating patterns in the emission zone or carousel like circulation above the polar cap. Giant pulses erupt from a few pulsars, especially the young and the rapidly spinning as spikes so bright and brief that they challenge both detector electronics and theories of coherence. These spikes line up with high-energy peaks and may arise where current sheets ripple and reconnect in a violent, intermittent way. The full structure is three-dimensional and time-dependent, and observations across many bands stitch pieces together. The Neutron star Interior Composition Explorer watches X-ray pulses from hotspots that shift with time, proving that magnetic footpoints and heating patterns move as currents rearrange. The Fermi mission maps gamma-ray light curves, whose double peaks and bridge emission match models with outer gaps or slot gaps, where particle streams graze the last open field lines near the light cylinder. The X-ray multi-mirror mission Newton and the Chandra X-ray observatory track wisps and knots in pulsar wind nebulae that ripple outward in arcs, each ripple an echo of changing outflow and reconnection, just beyond the frontier where field lines tear and rebuild. These external signatures talk to the star. When a pulsar switches radio modes from bright to quiet, the total spin-down torque sometimes changes by a few %, evidence that the global magnetospheric current system has reorganized. When a magnetar cracks its crust and twists its magnetic field, the torque can jump, and the X-ray spectrum hardens as the magnetosphere fills with heavier currents that scatter light. Torque changes, pulse shape changes, and spectral shifts make a coherent triad that says the exterior is alive, sensitive, and capable of multiple quasi-stable states. The shape of the beam evolves too, guided by the slow drift of the magnetic axis as the star cools and its interior couples on long timescales. Some pulsars show a secular change in profile that can be read as a gentle precession or as a rearrangement of currents that opens and closes parts of the radio cone. The breaking index measured over decades sometimes diverges from the simple value expected for a steady rotating magnetic dipole, a clue that the effective magnetic moment and the distribution of current change as the magnetosphere breathes. Close to the star surface, physics sets the boundary conditions for the flow. If the surface binds ions strongly as it might on a condensed iron skin, under monstrous fields, then charge extraction may be intermittent and patchy, which favours discharges that seed pair cascades above certain spots. If the surface is heated by returning currents, a corona of ions and electrons can form and feed the funnel. Hotspots that wander on kilometre scales imply that circuits close along different paths as the system searches for a configuration that satisfies global requirements with minimal dissipation. Farther out in the wind zone, the striped pattern of alternating magnetic polarity rotates with the star and carries energy as pointing flux, but reconnection gradually converts that field energy into particle energy and bulk motion. The efficiency of that conversion remains one of the open parameters, and its variation may explain why some nebulae shine so brightly in hard light, while others smoulder softly. The light cylinder is not a hard wall, but a threshold. Beyond it, field lines cannot co-rotate, so they open into a spiral that tightens with latitude and sends energy down a garden of paths. Current sheets beyond this radius become places where magnetic energy collects and releases in bursts. In numerical experiments, tearing modes grow there and islands of field break and merge a turbulent dance that might be the birthplace of the highest energy particles. Observations that catch rapid X-ray flares in some nebulae support the idea that reconnection not only shocks powers the brightest peaks. Meanwhile, the closed zone that hugs the star acts as a reservoir and a mirror. Waves excited by crustal motions can bounce their couple to the open zone and alter the charge density in the funnels. This coupling could help explain why some pulsars suddenly change mode or fall silent without a mechanical trigger. Magnetars push these behaviors to extremes by drowning the magnetosphere in twist. Their fields are so strong that the vacuum itself becomes birefringent, and the scattering of X-rays by charged particles trapped on field lines reshapes the emergent spectrum. Giant flares blow open the architecture eject clouds and leave the torque altered for months as the magnetosphere refills and untwists. Yet even ordinary pulsars show milder versions of these rearrangements, and the continuity across classes suggests a single framework that spans from quiet rotation-powered engines to quake-battered giants. All of this machinery powers winds that carry stress into the surrounding medium. Where those winds terminate in a standing shock inside a supernova, remnant rings and jets appear, and the location of the rings tells how the wind pressure balances the nebula pressure. The jets mark where the spin axis collates outflow, and their straightness or waviness records how stable the engine is. On longer timescales, the wind torch burns cavities in the interstellar gas and leaves bubbles that persist long after the central engine dims. The magnetosphere is therefore not only the origin of beams and pulses, it is the architect of a larger footprint that can be traced in light and in structure across many wavelengths and years. It responds to interior changes, it reorganizes itself, it feeds the nebula, and it evolves as the star spins down and cools. By watching its signatures from radio to gamma rays and by timing the way its states rise and fall, astronomers map an invisible structure with surprising precision, and every new irregularity is a corridor into physics that ordinary laboratories cannot reach. A pulsar wind begins near the magnetic poles, as a stream of charged particles flung outward by the rotating field, but it does not remain a narrow jet for long. As the star loses rotational energy, it launches a nearly continuous outflow that fills the inner volume of the surrounding supernova remnant, and then pushes against it until pressure organizes the encounter into a standing boundary called the termination shock. Inside that shock, the wind is still dominated by magnetic energy and by particles sliding along field lines in a pattern that remembers the rotation, so stripes of opposite polarity spiral outward, like bands on a slowly opening umbrella. At the shock, magnetic energy converts into particle energy. The flow decelerates, and electrons and positrons that once streamed almost freely are stirred into a turbulent sea where they can radiate across the spectrum. The immediate signature is synchrotron light, a broad glow that spans radio-optical and X-ray bands, and whose morphology often arranges itself into rings and jets that betray the geometry of the engine at the center. The Chandra X-ray observatory images reveal these rings as bright toruses, whose radii trace the pressure balance between the wind and the nebula bubble, while thin jets shoot from the axis, aligned with the spin sometimes straight and sometimes wavering as if the central engine's aim drifts with time. The Crab Nebula is the archetype, a luminous bubble where wisps arc outward and fade in a repeating cycle. Each wisp a ripple in the flow that travels from near the shock to the outer nebula in a matter of months. The Vela Pulsar Wind Nebula carries the same vocabulary in a different accent, with inner arcs that reconfigure and polarize light that maps the magnetic direction. Gaz-ray multi-mirror mission. Newton data show that the spectra of these features soften with distance from the center as high-energy electrons lose power to radiation, a radial aging that reads like growth rings and allows the flow time to be inferred. Optical images from the Hubble Space Telescope lay alongside radio maps from the Very Large Array to complete the history, while the Atacama Large Millimeter Array traces cooler electrons and sometimes the dust that rides the shock's breath. Farther afield, the high-energy stereoscopic system and other ground-based instruments catch very high-energy gamma rays from inverse Compton scattering as the same electrons climb in energy by bumping soft photons upward. Together, these views reveal a machine that converts rotational energy into a spectrum shaped by shocks, reconnection, and expansion. The pressure inside the bubble is not constant over the life of the system. At birth, the pulsar wind inflates freely into the ejector of the supernova, and the nebula grows as a sphere with bright inner structure. Later, the reverse shock from the outer shell, driven inward by the interaction of the remnant with the interstellar medium, returns to squeeze the bubble. This reverberation compresses the nebula, shifts the termination shock, and can warp the inner rings so the shape becomes a record of both the engine's output and the environment's push. In some remnants, the central star has been kicked so hard that it runs ahead of its own bubble. Where the motion through space is fast and the ambient gas is not too dense, a bow shock forms in front of the pulsar, and a narrow tail stretches behind a comet of charged particles confined by ram pressure. Optical images sometimes show a faint arc where neutral hydrogen is excited, while X-rays and radio follow the collimated tail that can extend for many light years. These bow-shock nebulae display stripes, knots, and side branches that change over years, a sign that instabilities ripple through the confined flow. Even when the star remains near the middle of the shell, the nebula inside is not quiet. Rings brighten, and dim jets wobble, and wisps drift outward in choreographed waves that are not perfectly periodic. The cadence depends on the balance between injected energy and the way magnetic fields tangle and reconnect. When a magnetar event injects twist into the magnetosphere, the nebular response can be sudden, as in transient radio nebulae that fade on timescales of years after a giant flare. Such episodes disclose a kinship between rotation-powered pulsars and magnetars, as if both tap a similar reservoir but with different gates and rhythms. The spectrum of a pulsar wind nebula carries practical diagnostics. The change of slope with energy tells how particles are accelerated and how quickly they cool. The break between radio and X-ray indices indicates where losses begin to bite. Polarization maps reveal the order of the magnetic field and show where turbulence has shredded it. Variability pinpoints where energy is currently being converted, because the brightest and fastest changing regions sit near reconnection layers or shocks. The Fermi Gamma Ray Space Telescope records high-energy photons that often correlate with structure seen in X-rays, linking the acceleration zones to the large-scale flow. When the Neutron Star Interior Composition Explorer times the hotspots on the star while the nebula flickers, researchers can track whether changes in the engine precede or follow changes in the bubble tying cause to effect. There remains a long-standing puzzle about how the wind shifts from electromagnetic dominance near the star to particle dominance in the nebula. Models begin with a high magnetization near the light cylinder, where the flow carries energy mainly in fields, yet the inner nebula seems to hold more energy in particle motion, a discrepancy that points to efficient magnetic reconnection, either at the termination shock or in the striped wind before it arrives. The repeated outward march of wisps in the Crab Nebula hints that sheets of current tear and merge in cycles that let energy cascade to smaller scales, where it becomes heat and particle motion. Alternative channels such as strong kinetic instabilities at the shock likely share the job. The efficiency of conversion probably varies with latitude, explaining why toruses and jets differ in brightness, with the torus showing where equatorial stripes die, and the jets marking where poloidal fields focus outflow and resist breaking. The interaction between the nebula and its surroundings also shapes how energy escapes into the galaxy. Some pulsar wind nebulae appear to leak particles that wander far beyond the main bubble, creating halos of very high-energy light that spread across dozens of light years. Whether these halos are common or tied to particular ages and environments is under active study because their presence affects the contribution of pulsars to the population of energetic positrons seen near Earth. If diffusion is slow around some objects, a pulsar can trap its particles longer and carve out a cocoon. If diffusion is fast, the same star can pollute a wider region with its accelerated charges. Measurements of the brightness profile at very high energies test these ideas and feed back into models of how turbulence and magnetic structures guide charged particles in the interstellar medium. Over centuries to millennia, the story of a pulsar wind nebula is one of growth, compression, and release. The central engine weakens as the star spins down, but the footprint of earlier vigor remains as a faint expanded bubble. In some cases, when the reverse shock crushes the nebula off-center, the relic bubble ends up displaced from the star, and later observers find a faint ghost that no longer surrounds its parent. In others, the star's motion leaves a string of synchrotron knots along its path as it inflates a tail in the passing gas. Each morphologic path is a logbook written in light. By reading the structure in radio-optical X-ray and gamma-ray bands, and by measuring how shapes breathe and how spectra age astronomers derive not only the present balance of pressures, but also the history of injection and the efficiency of conversion, the nebula becomes a calorimeter for the engine, and the engine becomes a probe of the medium together, composing a dialogue that ties inner magnetospheres to outer shocks, and threads a story from the kilometre scale of the polar cap to the light-year scale of the glowing bubble. Neutron stars spin like taut gyroscopes, Yet from time to time their rotation jumps forward by a tiny step, a sudden spin-up called a glitch, as if something inside a body harder than diamond has let go and passed hidden momentum to the crust. The timing record catches the moment cleanly. One observation shows a slightly long interval between pulses, the next shows a shorter one, and careful modelling reveals that the star has sped up by a fraction of a part in a million or less. Young pulsars are the most dramatic, and the Vela pulsar has become a teacher through repeating large events that arrive every few years, each followed by a recovery, in which the spin relaxes toward its former slope over days and months. The Crab pulsar shows smaller, more frequent jumps with a richer palette of post-glitch behavior, as if its interior holds a complex network of coupled parts. These steps are not noise. They are the fingerprints of deep physics and the most persuasive picture centers on a superfluid that lives beneath the crust. In that interior, neutrons pair up and flow without friction, and because the star spins, the superfluid must carry its angular momentum in a lattice of quantized vortices, microscopic whirlpools that pin to defects in the solid crust like tiny anchors. As the outer layers slowly lose spin to radiation and winds, the superfluid tries to keep up but is held back by pinning, so a lag grows between the superfluid and the crust. Strain accumulates quietly until a set of vortices unpins in an avalanche and rushes outward, handing angular momentum to the crust and making the whole star turn a little faster. The size of the step and the shape of the recovery curve encode how much of the interior joined the event and how quickly different components relock to the crust. The Neutron Star Interior Composition Explorer watches the associated X-ray pulses for subtle changes and has begun to map hotspots that wander or grow after a glitch, while the Chandra X-ray Observatory and the X-ray Multi-Mirror Mission Newton follow spectral shifts that might betray crustal heating. The possibility of heat is not only a detail. A second route to a glitch may begin with a starquake, a fracture in the rigid crust that adjusts the stellar shape and redistributes stresses in the magnetic field. A small change in oblateness alters the moment of inertia, and if the star becomes slightly more compact, conservation of angular momentum will drive a spin-up. In Magnetars, where the magnetic field can press the crust with irresistible force, bursts in hard X-rays and gamma rays sometimes accompany timing steps called glitches, and rarely anti-glitches, sudden spin-downs that hint at a torque impulse from a magnetosphere in violent rearrangement. The Fermi Gamma Ray Space Telescope and other high-energy monitors see the luminous outbursts, while radio telescopes track the rotation and witness profiles that change shape or vanish during the commotion, a triangulation that ties crust, magnetosphere and superfluid together in a single restless engine. Post-glitch behavior adds a second layer of clues. Some steps show an immediate partial recovery, a fast exponential relaxation that suggests a tightly coupled region just beneath the crust handed over angular momentum and then rejoined the spin down within days. Slower components relax over months as if deeper superfluid zones are connected by weaker mutual friction. The fraction that does not recover becomes a permanent revision to the spin, and over many glitches that permanent part can add up to a meaningful fraction of the total loss to radiation, implying that interior transfers help the star dispose of its stored angular momentum more efficiently than a smooth break alone would allow. Microglitches, tiny steps in either direction, appear in some stars, and may be the surface trace of small-scale unpinning avalanches or local current changes in the magnetosphere that tug the crust for a heartbeat. Mode switches sometimes bracket a glitch with the radio emission, changing personality and the measured spin-down torque, shifting by a few percent a correlation that argues for global reorganization of currents during or after the event. The tendency for the youngest and warmest pulsars to glitch with larger steps suggests that temperature and impurity content matter because they set the strength of pinning and the ease with which vortices move. Theoretical work predicts that the inner crust, where nuclei may arrange as rods, and sheets known as nuclear pasta, could anchor vortices in a way that promotes collective failure, so that a trigger in one patch cascades across a region like falling grains in a pile. If that cascade shakes the crust, elastic waves can ride into the magnetosphere and modulate radio emission, a possibility supported by pulse shape changes in the wake of some events. The discipline of glitch hunting turns the sky into a laboratory where repeated trials unfold over years. Long campaigns with the Parkes telescope, the Green Bank telescope Meerkat, and the 500-meter aperture spherical telescope measure pulse times with precision and catch the steps even when they are small building statistics on waiting times and size distributions. Those distributions often look like power laws, a signature of self-organized criticality, as if the interior lives near a balance where any small push can free a hierarchy of avalanches. Not every neutron star plays the same game. Some show decades with no events, others rattle often. Millisecond pulsars being older and cooler, and having had their spins polished by past accretion rarely glitch, and when they do, the steps are tiny, an outcome that fits with a thinner pinning layer or a more tightly coupled core. Central compact objects in supernova remnants, which may have buried fields and unusual thermal maps, sometimes drift without sudden steps hinting at unique interior structures. Magnetars disrupt the pattern with fewer but more complex events. Their timing can lurch during radiative outbursts, and the torque can remain altered for months after a flare, as if twisted magnetic loops hold the exterior in a different state that slowly relaxes. In a few cases, a magnetar has shown an anti-glitch, a sudden slowdown that perhaps reflects a magnetic storm that added braking, or a reconfiguration that swept the beam away from the best view. The Laser Interferometer, Gravitational Wave Observatory, Virgo and Kagra collaborations have searched for brief gravitational waves associated with the largest magnetar flares or with giant glitches, hoping to catch a ringing mode excited by a quake. So far the searches have set limits, but those limits already prune models of how the crust and core vibrate. There is also speculation that certain oscillation modes called R modes could be excited during or after a glitch and then damp by emitting gravitational waves, a process that would alter the recovery in a way timing arrays might eventually see. Each of these threads ties a small rotational step to a broader chain of cause and effect. A glitch is not an isolated hiccup. It is the moment when stored differences are reconciled, when a superfluid communicates with a lattice, when magnetic stresses and crustal flaws negotiate a temporary peace. It is a reset that preserves the clock but writes new information into its face. By stacking many events across many stars, observers and modelers attempt a tomographic reconstruction of matter under pressure beyond terrestrial reach. They ask how strong the crust is before it fails. They ask how quickly the core responds when the outer layers change speed. They ask whether the very densest cores dissolve into quark-rich phases that couple more or less tightly to the rest. The answers come slowly through timing lines drawn across years and through sudden steps that punctuate those lines. Each new glitch is another tap on the bell of a small, hard world, and although the sound is faint, the instruments have learned to listen, to compare, and to build a shared story in which creaks, cracks, and whirlpools together define the living mechanics of the densest steady engines in the universe. Modes, nulls, and noise turn the simple idea of a steady lighthouse into a living weather map where the beam can harden soften, split, fade, or vanish, and where the engine's torque itself shifts as if the atmosphere of charged particles around the star has changed its mind. A mode is a repeatable personality of the pulse shape and brightness that persists for minutes to hours, and sometimes for days, then yields to another personality with a near instantaneous switch. In one mode, the main peak may sharpen, and a trailing shoulder may grow. In another, the shoulder collapses and a softer bridge lights the gap between components. The integrated profile that once looked unchanging becomes a composite of such states, and when observers separate pulses by state order, appears from the apparent chaos. Nulls bring deeper mystery. In a null, the radio beam falls silent for a span from a few rotations to many thousands, after which emission resumes as if a valve has been opened. Some stars show nulling fractions that approach half of their time on the sky, and a few enter an intermittent regime where the radio turns off for weeks, while the spin down slows, then turns on, and the break strengthens again, a clear sign that particle outflow and current closure regulate the torque on the crust. The linkage between emission state and rotational slowdown is one of the cleanest proofs that the magnetosphere can reorganize globally, because the vacuum dipole torque alone cannot jump by that much. Subpulse drifting adds another layer. In many pulsars, the single pulses are not simple spikes, but a train of subpulses that march across the window in diagonal bands when stacked by rotation, as though bright patches circulate above the polar cap on a carousel. The drift rate can change with mode, the number of patches can differ between states, and the pattern can pause or reverse, hinting that the electric fields that steer plasma near the surface are not fixed by geometry alone, but respond to the total current system that threads open and closed field lines. Polarization tracks those changes with surgical sensitivity. The sweep of linear polarization position angle through the pulse can follow the classic rotating vector signature of a dipole, and then at a boundary between components jump by 90 degrees as one polarization mode gives way to another. The fraction of circular polarization can flip sign across the beam, and its changes with mode suggest that the plasma density and birefringence in the emission zone vary as the magnetosphere changes state. Farther out propagation through the interstellar medium adds its own modulation through scintillation, but careful multi-frequency campaigns separate that extrinsic twinkling from intrinsic behavior, and what remains points back to the star. Timing noise threads all of this, a low-frequency wander in pulse arrival times that cannot be removed by simple spin-down models. In young pulsars, the noise can be large and may reflect both interior and exterior processes. One view assigns part of the red noise to random walks in torque as the magnetosphere switches between metastable current patterns. Another ties it to the interior, where superfluid regions couple and decouple, with a spectrum of timescales producing small cumulative shifts in rotation that look like wander rather than steps. In some stars, the noise is not entirely formless. Quasi-periodicities appear long cycles that could be compatible with free precession of a slightly aspherical star or with cycles in magnetospheric loading and release. Claims of true precession are debated because superfluid pinning can damp wobble, yet a small slow precession is not excluded, and gradual profile evolution over years suggests that the spin and magnetic axes may not be perfectly locked. Mode changing is not confined to radio. In a few sources monitored with the X-ray multi-mirror mission, Newton the X-ray brightness and spectrum shift in concert with radio mode switches, as if hotspots grow or migrate when the magnetosphere rethreads its currents. Such multi-band correlations point to a feedback loop from the exterior to the surface. Returning currents heat the polar caps. The surface emission hardens or softens, and the altered supply of charges launched from the cap in turn reshapes the magnetospheric state. The Neutron star interior composition explorer refines this picture by tracking tiny shifts in X-ray pulse phase and amplitude during state changes, watching hot regions brighten, fade, or move by a few kilometres across the surface. Coherent radio emission itself remains a frontier. The requirement that charges move in step invites theories that start with streaming instabilities, bunch formation, and master-like growth along open field lines. But the same star can show ordinary pulses microstructure at microsecond scales, drifting subpulses with strict order, and rare giant pulses that are so bright and so brief that they brush the limits of coherence and invoke reconnection in current sheets near the light cylinder. The magnetospheric state that favours one regime may suppress another. When a pulsar falls into a long null, the pair creation engine may be quenched because the accelerating gap fails to reach the conditions for copious pair production. Changes in surface temperature at the polar cap, perhaps induced by earlier current patterns, can shift that threshold so that the star toggles between a pair-rich bright regime and a starved quiet regime. The death line that marks where radio emission ceases in parameter space is less a hard boundary than a contour that moves with geometry, temperature, and field configuration. And this mobility explains why very long-period emitters can sometimes break the rule and shine. Low-frequency arrays have found sources with periods of many tens of seconds that fire sporadically, perhaps because a temporary resurgence of pair production allows bursts, or because the beam is narrow and only grazes Earth now and then. At the other extreme, a subset of young and very fast pulsars emit giant pulses aligned with high energy peaks, a connection that ties the strongest radio flashes to the regions near the light cylinder, where fields swap partners and accelerate particles in abrupt surges. Intermittent pulsars reveal another rhythm that lives on timescales of days to months. Some switch on with a bright, stable profile and a strong torque, then switch off almost entirely with a weaker torque, as if a global current circuit has opened. The transitions can be quasi-periodic and show advance warning in subtle profile changes. A few stars show a three-state ladder of torques and profiles, and in those state fractions shift slowly over years, as if the engine explores a small landscape of attractors that move with age. The mapping of these states benefits from coordination across facilities. Park's Green Bank Meerkat and the 500-metre aperture spherical telescope watch the radio pulses and collect polarization, while the Fermi Gamma Ray Space Telescope keeps a ledger of high-energy photons. When a state change is caught in radio, and a change in gamma-ray flux follows or precedes, the relative timing constrains where in the magnetosphere the reconfiguration began. Bow-shock nebulae sometimes flicker in step with long nulls, hinting that the particle outflow can weaken enough to alter the pressure balance at the termination shock, though this link remains provisional. Theoretical efforts use global magnetohydrodynamic models that allow for resistivity and pair creation to seek self-consistent state changes. In those experiments, the magnetosphere can settle into multiple force-balance solutions with different current distributions. Small changes in pair supply or boundary conditions tip the system between them, reproducing torque jumps and profile shifts without altering the underlying magnetic dipole. Kinetic simulations of current sheets beyond the light cylinder show reconnection that is inherently bursty, a feature that would feed variability into the radiation pattern and perhaps seed giant pulses. Close to the surface, models that include partial ion binding and hotspot feedback produce drifting patterns and mode switching as the accelerator near the cap breathes. The combined view suggests that modes, nulls, and noise are not separate curiosities, but expressions of a single coupled system that includes surface magnetosphere and wind. The wonder is that a star that would seem to be the most rigid object is also among the most variable. Through this variability, the engine announces its sensitivity to small internal and external changes, and by collecting long records of state sequences, waiting times, and torque levels, observers build transition matrices that can be compared with models. Each entry in such a matrix is a probability that the star will go from one personality to another in a given time, and the probabilities evolve as the star ages. This is not randomness without memory. It is a weather pattern whose statistics are clues. The same neutron star that keeps time to parts in a million also daydreams and storms, and in its moods it reveals the wiring that turns rotation and magnetism into light. Magnetars stand apart as neutron stars whose magnetic fields reach such strength that even empty space behaves like a medium, and light travels differently, depending on how it aligns with the field, and this extremity transforms the usual rotation-powered engine into a tension-powered system where stresses pile into the crust and snap, with consequences that race across space. A magnetar turns with periods of a few seconds rather than fractions of a second, not because it was born slow, but because magnetic braking siphons away spin energy with unusual efficiency, and over thousands of years the period grows while the magnetic field inside and outside the star stores energy, the way a twisted spring does. The surface field measured from timing may already be enormous, yet the true burden can be larger if internal fields are wound tight beneath the crust, and the mismatch between inside and outside becomes a source of stress that slowly distorts the rigid lattice until faults reach a critical point. When a fracture runs, magnetic loops anchored in the crust can be jerked and reconnected, and charged particles trapped on those lines are suddenly accelerated to high energy, flooding the surroundings with hard X-rays and gamma rays. The Fermi Gamma Ray Space Telescope, the Neil Gehrels Swift Observatory and other high-energy sentinels have recorded bursts that last a fraction of a second to many seconds, and on rare days the energy release swells into a giant flare that can light up detectors from across the galaxy. On a day in late December in the year 2004, a magnetar in a distant spiral arm released a spike of gamma rays so powerful that satellites across Earth registered saturation, followed by a decaying tail modulated at the spin period, an event that announced what a magnetar can do when its magnetic architecture breaks at scale. The rise was almost instantaneous, as if a magnetic cage had been sprung and currents had rearranged in a heartbeat, and the tail told that a trapped fireball of pairs and photons had become confined by closed field lines and then leaked away as the star rotated. Other giant flares have appeared from nearby galaxy companions, carrying the same pattern of a sharp spike and a long pulsing afterglow, and together they draw a picture where magnetic reconnection and seismic motion form a coupled system. Between such crescendos, magnetars show storms of smaller bursts that climb into hundreds of events over days, a soft gamma repeater phase in which the crust may be groaning along many faults while the magnetosphere fills with twist. In these episodes, X-ray spectra harden as resonant scattering by charges in the magnetosphere smears and boosts the light, and the total torque on the star can rise as extra current threads open field lines, proving that the exterior architecture has changed. The X-ray multi-mirror mission, Newton and the Chandra X-ray Observatory, track the hotspots that wander across the surface as returning currents deposit heat, and the Neutron Star Interior Composition Explorer sees pulse profiles that grow more complex as if new loops have been draped above the surface and are radiating back. In the fading tails of the largest bursts, subtle ripples known as quasi-periodic oscillations appear as brightness wiggles at specific frequencies and these may trace global seismic modes that ring the crust and core after a quake. If so, then a timing analysis of brightness waves becomes a form of starquake seismology that could reveal how thick the crust is and how tightly the superfluid within couples to the lattice. The laser interferometer, gravitational wave, observatory, Virgo and Kagra have hunted for gravitational waves that might accompany such modes, and while upper limits have so far led the way, those constraints already cut into some possibilities for how the interior vibrates. Magnetars also link to fast radio bursts the millisecond spikes of radio light that arrive from beyond our galaxy, and that carry dispersion measures that point to great distances. In the year 2020, a known magnetar in the Milky Way produced a bright radio burst coincident with an X-ray burst pairing that demonstrated at least one concrete pathway from magnetic reconnection or crustal failure to a coherent radio flash. Not all fast radio bursts must be magnetar-borne, but the connection opened a channel where theories could be anchored to an object with a name and a distance. The radio machinery in this scenario may live near a current sheet where magnetic fields reconnect and launch particle beams that drive a massa-like process in an expanding shock, or it may live near the surface where a gap is briefly overfilled by a sudden surge of charges. Either way, the lesson is that a magnetar stores energy in both elastic and magnetic reservoirs and can pay it out across the spectrum in linked ways. Even in quieter phases, magnetars differ from ordinary pulsars. Their thermal X-ray emission often shows large hot regions that fade slowly as twist relaxes, and their timing can wander with a red noise that reflects ongoing friction between interior and magnetosphere. Some radiomagnetars switch their radio profiles and polarization states as their X-rays wax and wane, offering a direct handle on how magnetospheric currents bend both coherent and incoherent radiation. A few objects blur class boundaries by showing magnetar-like outbursts from stars whose measured spin-down fields are modest, which suggests either that deep internal fields can store energy without advertising at the surface, or that intermittent mountains of twist can mimic an extreme magnetic moment. The discovery of low-field magnetars widens the landscape and forces models to consider how buried fields or relic toroidal components might lurk for centuries and then rise. Surface physics at a magnetar also enters unfamiliar territory. The atmospheric layers may condense into a metallic skin under the combined pressure of gravity and magnetic field, altering the emission pattern and polarization. Vacuum birefringence can imprint a strong linear polarization that modulates with spin, and new X-ray polarimeters are designed to read this signal and test quantum electrodynamics in a natural laboratory. Deep inside the equation of state controls the shear modulus of the crust and the response of the superfluid core to strain. If deconfined quark matter or other exotic phases occupy the center, the way the star rings after a quake could differ in measurable ways, and the recovery of spin after a timing step might reveal a different balance of coupled components. Surrounding all this is a magnetosphere that does not simply scale up from a normal pulsar, but enters a regime where plasma density and geometry allow multiple force balance solutions. Twisted loops can trap particles' heat surfaces and exert extra torque for months. Eventually, radiation and reconnection unwind the twist, and the engine slopes back toward a quieter state, yet few magnetars return to exactly what they were. Their histories show scars. Profiles and spectra retain offsets as if a healed bone still knows the break. The environment around a magnetar registers the outbursts as well. Transient radio nebulae have followed giant flares as shells of energized particles expand and fade, and the size and brightness of these shells constrain the total energy released, and the efficiency with which magnetic energy becomes particle motion. In some cases, nearby dust scatters the X-ray flash into rings that expand with time, yielding a light echo that reveals the distance to the dust and to the source. Such echoes let observers convert a violent day into a geometric ruler. Across all of these manifestations, the same rhythm holds data to anomaly, to mystery, to speculation. The data say that magnetars exist and burst and flare and ring. The anomalies are the giant flares that rise too quickly, the timing steps that do not fit simple rotational braking, the radio flashes that appear beside hard X-rays. The mystery lies in how magnetic tension and crustal strength weave a schedule for failure, and in how currents organize in a geometry that feeds both coherent and incoherent light. The speculation points to deep fields coiled beneath the crust, to phases of matter where neutrons yield to more fundamental constituents, and to magnetospheres that admit several stable personalities. A magnetar is therefore not only an extreme neutron star, it is a proving ground for physics of fields and matter under conditions that no laboratory can build, and each burst, flare, and afterglow becomes a sentence in a long instructive confession that is still being written. From the crust to the core, a neutron star is a stack of regimes where matter changes character under pressure that refuses compromise, and each layer leaves distinct marks on heat, magnetism, and rhythm. The outermost skin is an atmosphere only a few centimeters thick, a veil of ions and electrons that imprints color and polarization on escaping light. If accretion has delivered light elements, the atmosphere radiates efficiently, and the spectrum hardens. If iron and heavier nuclei remain, the glow is softer, and lines blend into a smooth, magnetically shaped continuum. In magnetic fields measured in trillions of times, the strength found near Earth atoms stretch into spindles, and opacities shift so the same surface can appear different to instruments that separate light by energy and by polarization. Beneath this skin lies the envelope, a transitional layer that controls how interior heat reaches space. Its composition acts like a thermostat. Light elements let heat through more easily, heavy elements throttle it, and a buried magnetic field channels the flow toward the poles, making hot caps that drift and brighten over years as the field reorganizes. Below the envelope, the outer crust begins a crystal of heavy nuclei, arranged in a lattice soaked in a sea of degenerate electrons that carry current and conduct heat. Pressure squeezes electrons to higher energies, while nuclei become more neutron-rich, and at depths of hundreds of meters the balance tips. Neutrons begin to drip from nuclei and fill the spaces between them. This marks the inner crust where a rigid lattice of nuclear clusters coexists with the neutron superfluid. Here geometry matters. As density rises, nuclear clusters compete with the pressure of the sea around them and with their own electric repulsion, and the compromise can force matter into rods and slabs poetically called nuclear pasta. These shapes change how the crust resists shear, how it conducts heat, and how it guides magnetic fields. They also provide new anchor points for the vortices that thread the superfluid. The inner crust sets the ledger for angular momentum. A rotating superfluid carries spin in quantized vortex lines, and those lines wander through the lattice. They can pin to nuclei, hold fast for years, and then unpin in cascades that move angular momentum outward. When the outer layers have slowed to a pace that diverges from the pace held by the pinned fluid, a threshold is crossed. Vortices let go sweep through the crust, and the star spins up by a tiny step called a glitch. The size of the step and the shape of the recovery curve tell how strongly vortices pinned, how many layers took part, and how tightly the core and crust are coupled. If neutrons are partially trapped by the lattice, a phenomenon called entrainment, the free superfluid that can join a glitch is smaller than it looks, and other reservoirs perhaps in the core must contribute. This same fabric governs quakes. As magnetic fields drift in the crust, Hall drift slides currents sideways and piles stress into corners, while slow electrical diffusion smooths away the smallest structures. When the crust cannot bear more, it fractures or flows, releasing heat into the surface and waves into the magnetosphere. In ordinary pulsars, the result may be a mode change and a small torque shift. In magnetars, the same process runs hot with bursts and flares that rearrange the exterior and leave scars in profiles for months. At greater depth, the lattice dissolves and the outer core begins. Here neutrons dominate, but a fraction of protons and electrons share pressure and carry charge. Temperatures fall enough that neutrons pair and flow as a superfluid, while protons pair and become a superconductor. Two families of threads then fill the liquid vortex lines that store rotation in the neutron superfluid and magnetic flux tubes that carry the internal field in the proton superconductor. Where these families cross, they can pin or slide, and their friction or freedom sets how quickly the core responds when the crust changes speed. If vortices drag against flux tubes, the interior couples tightly, and a glitch relaxes quickly. If they slip, the interior is slow to follow, and the recovery stretches across months. The core is also the furnace that sets the long cooling arc. Neutrinos carry energy away through reactions where neutrons turn into protons and electrons or the reverse, while emitting light particles that escape freely. If the fractions of particles cross a threshold, a direct route opens and the star chills fast. If that threshold is closed by composition, the path is slower. Pairing of neutrons and of protons modifies both cases, suppressing reactions by gapping the energy levels while also igniting a brief efficient channel when pairs first form and break. The effect is visible in cooling neutron stars that fade at different rates, and in transient systems that heat during accretion and then relax their light curves, betraying what pathways ran in the dark. Deeper still lies the inner core, a region of greatest uncertainty. At several times, nuclear density neutrons may no longer remain intact. They could dissolve into deconfined quark matter, perhaps in color, superconducting phases that carry current without resistance. Alternatively, a mixed phase could form with droplets or rods of quark matter immersed in neutron-rich fluid, the last echo of nuclear pasta carried to higher pressure. These possibilities change how compressible matter is. If the equation of state softens, the star squeezes smaller for the same mass. If it stiffens, the star swells larger. Observations weigh in. The Neutron Star Interior Composition Explorer maps hotspots and pulse shapes, and infers radii that paired with masses from radio timing or from the Shapiro delay in binaries cut away swathes of theoretical options. The Laser Interferometer, Gravitational Wave Observatory, and its partners read tidal deformability during mergers and translate the gentle stretching into limits on how easily a star yields. Together, these constraints narrow corridors where any exotic core must live. Magnetism threads every layer. In the crust, currents carried by degenerate electrons wander under the push and pull of Hall drift, moving magnetic power from broad structures to finer ones. Ohmic diffusion then turns the finest filaments into heat. The pace depends on temperature and impurities, so a young hot star rewrites its field quickly, while an old cold one preserves a memory of youth. In the core, the proton superconductor corrals magnetic field into flux tubes. Over long times, these tubes can creep, driven by buoyancy and by drag with moving vortices, and their motion can alter the large-scale dipole that sets how the star spins down. If a toroidal bundle of deep field rises into the crust, the exterior can feel a surge and the braking can change. If a bundle sinks, the surface can quiet. These slow acts play out over thousands to millions of years, yet their traces are legible in the long timing records that show braking indices that wander from the value expected for a simple dipole. Elastic strength gives the crust a seismic voice, while fluidity gives the core its ability to ring. Global oscillation modes can be excited by quakes or by magnetic rearrangement. Torsional shear modes depend on crust thickness and composition. Alphen modes depend on field strength and geometry. Faint ripples in the tails of giant flares hint at such modes, and their frequencies promise astroseismology of small dense worlds. If the crust sustains a tiny mountain only centimeters high, the star can radiate a continuous gravitational wave during rotation, a quiet whistle that detectors seek in targeted searches toward known fast rotators. The presence or absence of such a signal would speak to the crust's ability to hold shape under relentless centrifugal and magnetic stress. Heat field and spin are not separate themes. Heat changes conductivity and thus field evolution. Field evolution reshapes the magnetosphere and thus torque. Torque changes vortex dynamics and thus glitch behavior. Vortex dynamics change heating and thus the thermal map. This loop means that the star is not a static onion but a living circuit. Instruments close the loop from outside. Pulse profiles and polarization map magnetic architecture. Spectra in X-rays and soft light trace temperature patches and cooling routes. Timing lines write the history of stresses released and stresses stored. Gravitational wave events weigh deformability during mergers. Step by step, these surveys push the interior from speculation toward measurement. Yet even as corridors narrow, the unknown keeps a foothold. The lattice may hide defects born in youth that guide future failures. The superfluid may thread a patchwork where pinning strength varies by orders of magnitude across kilometres. The core may mix phases that couple tightly in one decade and loosely in the next as temperature falls. The star remains a layered engine whose hidden parts govern the flashes we see, and the path from the crust to the core is the path by which those hidden parts lend their voice to light, to timing, and to the faint flecks of space-time itself. Superfluids and vortices give a neutron star a second hidden rotation, a ghostly spin that lives beneath the crust and in the core, moving with a logic that does not belong to ordinary fluids, and yet dictates when the visible crust will hurry or pause. In the outer layers, where nuclei form a lattice soaked in a sea of degenerate electrons, neutrons begin to pair as the temperature falls and the density rises, and those pairs condense into a superfluid that can flow without friction and carry momentum in discrete packets. Because a superfluid cannot rotate like a rigid body, it chooses instead to seed itself with slender filaments of quantized circulation vortex lines, spaced so that the average flow mimics a smooth spin. The number of lines depends on the rotation rate, and as the star slowly loses angular momentum to radiation and winds, the array must thin. Vortex lines therefore migrate outward in a long, patient drift that keeps the invisible fluid in step with the crust unless something holds them back. The lattice supplies the anchors. Vortex cores can pin to nuclei in the inner crust, lodging at imperfections or at the structured pasta, where rods and slabs of nuclear matter create natural shelves. Pinned vortices halt the outward march and let a lag grow between the superfluid and the crust. The lag is tension stored as differential rotation, and when the pinning web fails at some threshold, a rush of unpinning allows vortices to slide outward, handing angular momentum to the crust in a step that observers register as a glitch. Not every vortex moves at once. Theory and the timing record both favour avalanches that begin with a few lines and recruit neighbours, creating cascades of many sizes. Between large failures, a small trickle of motion known as vortex creep allows thermal activation to wiggle lines past barriers, producing a slow, steady leakage that helps set the long-term spin down. Temperature and composition govern this creeping pace. In a warmer young star, thermal kicks are generous and the creep is lively. In a colder old star, the creep is sluggish, and the stress can mount for years without relief. Where vortex lines are free, they do not move as stiff rods. They can bend into ripples called Kelvin waves. They can tangle when flows collide, and they can enter states of quantum turbulence, where a forest of lines knots and unknot in a restless exchange that dissipates energy into heat and into tiny sound-like pulses within the superfluid. If turbulence blossoms during a large unpinning, the relaxation after a glitch may follow a broken set of timescales, rather than a single clean exponential, and the noise in the spin can carry a memory of the tangle as it dies away. Mutual friction links the superfluid to the normal components. Electrons scatter off the magnetic structures that thread vortex cores, and that drag acts as a brake that transfers momentum between fluids. In the outer core, where protons are expected to pair into a superconductor, the magnetic field gathers into quantized flux tubes, and neutron vortices can snag on these tubes as well. Where a vortex meets a flux tube, they can pin cross or slide depending on angle and local conditions, and the outcome sets the timescale on which the deep interior follows a change in crustal speed. If pinning within the core is strong, the superfluid resists being dragged, and a post-glitch recovery can take months to settle. If it is weak, the coupling is fast, and the star relaxes in days. The interplay of vortices and flux tubes also decides how magnetic fields evolve, because pinned structures can carry field with them or grind against it, letting buoyancy and drag reshape the interior magnetism over long spans. The two-fluid nature invites oscillations that have no counterpart in ordinary stars. There are modes in which the superfluid and the normal fluid slide past each other, modes in which they ring together, and modes that become unstable when rotation, temperature, and mutual friction fall into special alignments. Among these, a family called R modes, in which the restoring force is the Coriolis effect of rotation, can grow by emitting gravitational waves if viscous damping and mutual friction are weak enough. A star that spins above a threshold might then shed angular momentum through a quiet hum of spacetime, slowing until the instability shuts off. No firm detection has yet surfaced, but timing of the fastest millisecond pulsars and searches by the Laser Interferometer, Gravitational Wave Observatory and its partners have already carved away parts of the plane where such growth would be easy nudging models toward higher damping or stronger coupling. The superfluid also writes on the thermal map. Pairing opens an energy gap that suppresses neutrino emission, cooling the star more slowly, but when pairs first form, they break and form again in a frenzy that floods the interior with neutrinos and briefly accelerates cooling. Observers watch neutron stars in quiescent low mass. X-ray binaries cool after accretion episodes, and they compare the slope of the fading light with models that include superfluid transitions. A match argues for pairing strengths and critical temperatures in ranges that then feed back into glitch models, because the same microphysics sets the pinning strength and the creep. In Magnetars, where the crust and the field exchange stress with unusual vigour, the superfluid can be dragged into unfamiliar territory. A quake that shakes the lattice may free vortices locally, and the resulting redistribution of angular momentum can join the magnetic torque to produce an irregular sequence of timing steps and red noise. Heat from repeated starquakes warms patches of the crust, raising the creep rate beneath them, and altering the shape of later events such that a magnetar that has stormed for months can show a softened spin down before it calms. The connection runs both ways. A redistribution of vortices can change surface heating patterns by altering the return currents that close the magnetospheric circuit so that hotspots mapped in X-rays wander in sympathy with timing changes tracked in radio. Laboratory analogues lend metaphors without copying the conditions. Liquid helium shows quantized vortices, Kelvin waves reconnections and turbulent tangles. Ultra-cold atomic clouds allow tuning of interactions and trap geometries to mimic pinning and unpinning. These systems do not reach nuclear densities or carry magnetic fields that bend the vacuum, yet they teach how a superfluid stores and releases rotation, and how turbulence changes the rules for transport. The neutron star inherits these behaviors and complicates them with stratification, elasticity, superconductivity, and gravity that imprison all actors in a tiny world with the mass of a sun. The timescales therefore range from microseconds for a Kelvin wave to travel across a micron to years for a creep front to cross a kilometre. Observers catch only the integral effects, and the art is to invert coarse timing and spectral data into fine interior narratives. Millisecond pulsars being old and cold show that superfluids can remain placid for eons, with pinning so weak or coupling so strong that glitches are rare and tiny. Young pulsars warm and impure rattle, often as if vortices stick at many thresholds, and the landscape of pinning strength is patchy. Different regions may act alone or in concert, and this patchwork can explain why waiting times for large events in the Vela pulsar cluster around a few years, while the Crab pulsar throws many small steps in quick succession. The superfluid carries memory in its vortex map, and each event rewrites that map, changing the initial conditions for the next failure. Precession, if present at even a tiny level, could tilt the array and move pinning sites in and out of reach on long cycles, injecting quasi-periodicity into timing noise. Deep in the core, if matter yields to more exotic phases such as deconfined quarks in colour, superconducting states, the response to rotation and to magnetic structures could change again. Some phases may not pin vortices at all. Others may pin so strongly that motion becomes jerky and rare. The gravitational wave signature of a merger speaks to how deformable such interiors are, but the daily behavior of a single star speaks to how they let momentum travel. The two views meet when a merger remnant survives briefly as a hypermassive neutron star. In that short life it rotates wildly, seeds a dense thicket of vortices, and drives magnetic fields into a storm that may set the initial map for any neutron star that emerges. In the quiet decades that follow, mutual friction, creep and turbulence smooth that inheritance into the slower rhythm of an ordinary pulsar, and the glitches that punctuate that rhythm are the audible clicks of the hidden gears. The picture that grows from all of this is not of a rigid clock with defects. It is of a layered quantum mechanical engine in which the most gentle flows decide the most dramatic stumbles. By measuring the steps and the relaxations, the offsets and the wander, and by setting those against maps of hotspots and variations in torque astronomy, learns to read a language of vortices and flux tubes of creep and coupling that translates rotations into matter's behavior near the limit of what can exist. Quarks at the threshold enter the story when pressure climbs beyond the comfort of neutrons packed shoulder to shoulder, and the familiar building blocks of nuclei begin to blur into their constituents, and the star that seemed merely dense now asks whether it hides a new phase of matter that no laboratory can hold, the equation of state. The relationship between pressure and density is the grammar of this interior, and its shape decides whether the star swells or shrinks for a given mass, whether sound crosses the core briskly or grudgingly, and whether a central region melts into deconfined quark matter that carries current in forms unlike anything on Earth. Observations carve at that grammar from many sides. Timing of binaries weighs neutron stars with exquisite accuracy when the dance is tight, and relativistic delays mark the path of light, and several pulsars now tip the scale near 2 solar masses and perhaps a little more, which already tells that the pressure at a few times nuclear density cannot be too soft. The Neutron Star Interior Composition Explorer adds radii by reading the way hotspots on a spinning surface modulate X-rays as gravity bends light, and those radii paired with masses restrict how compressible the core may be. Gravitational wave detections of merging neutron stars measure tidal deformability, a quantity that describes how easily a star is stretched by a companion's field. And when the Laser Interferometer Gravitational Wave Observatory Virgo and Cagra extract this property from the phasing of the waves, they place boundaries on how stiff or soft matter can be. A purely stiff equation swells stars and yields high deformability that data do not favor. A purely soft equation collapses radii and forbids heavy stars that timing proves exist. The narrow corridor left between these demands invites a change of state in the middle, a phase transition that softens the core while leaving the outer layers stout enough to support weight. Such a transition could occur when neutrons and protons lose their identity, and quarks roam in a sea that may itself become ordered pairing into color, superconducting states that flow without resistance. If this happens gently over a range of pressure, the mass and radius vary smoothly. If it happens sharply, a plateau or kink enters the curve and 2 stars with the same mass but different radii become possible, a twin branch that will be the clearest astronomical fingerprint of new matter. The search for that signature runs through many channels. Post-merger remnants ring in gravitational waves at frequencies set by the stiffness of the core, and a sudden softening should imprint a shift in the dominant tone as the central density crosses the transition. Numerical experiments show that the hot differentially rotating remnant either collapses quickly into a black hole or survives for many milliseconds to seconds as a hypermassive neutron star, and the dividing line depends sensitively on the hidden pressure. The electromagnetic counterpart, the Kilonova, glows as freshly minted nuclei decay in ejected debris, and the color and duration of that light depend on how much matter is flung out and how neutron-rich it is. A core that softens early may deform differently and expel material along paths that change the balance of heavy elements, so the spectrum of the kilonova becomes a circumstantial witness to the core. The European Southern Observatory and space observatories compile these light curves, and spectra and models iterate toward the interior by matching color speed and mass of the ejector. Cooling offers another lever. Neutrinos carry heat from the center for thousands of years, and if quark matter opens rapid channels for neutrino emission, a star that hosts such a core can cool faster than a neighbor without it. The X-ray multi-mirror mission. Newton and Chandra monitor isolated neutron stars whose temperatures fade with age and transient systems that heat by accretion, and then cool when feeding pauses provide controlled experiments. A faster-than-expected slide could hint at new species in the core, though crust composition and superfluid gaps also play roles, so this route requires care. Glitches, those sudden spin-ups, may whisper about the boundary between a nuclear shell and a quark heart if the interface pins vortex lines or channels their motion in distinctive ways, but the link is indirect and tangled with crust physics. Magnetism carries clues as well. If protons in the core are superconducting the magnetic field threads, quantized flux tubes, and if quark matter carries current differently, the field may pin or drift with different rules. Over very long times, this could change the evolution of the large-scale dipole and the slow drift of breaking index, but such signatures emerge only by comparing long histories across many stars. A more direct laboratory would be a star that just brushes the maximum mass allowed by its interior. If a measured mass landed significantly above two solar masses, with a radius not too large, pure nuclear models would feel fresh pressure to harden while allowing a qualitative change at higher density to keep the whole sequence stable. The habit of nature so far is to permit heavy stars while keeping radii modest, a combination many theorists find suggestive of a core that is softer than nuclear matter would be if left to its own devices. The possibility that quark matter is not merely a phase but the true ground state of matter gives a more speculative branch called strange matter, in which a balance of up, down and strange quarks yields a configuration more bound than iron. If nature favoured this state, entire stars of quark matter could exist self-bound and clothed in a thin nuclear skin with mass-radius relations that differ enough to test in principle. Searches for distinctive seismic modes, cooling patterns, or spin evolution have not secured such a case, and the safer view is that if quark matter appears, it shares the star with nuclear layers in a hybrid configuration whose centre holds the novelty. Even there, the type of colour, superconductivity matters. Pairing patterns decide heat capacity, neutrino emissivity, and magnetic response. Some phases expel magnetic field as a superconductor does others, let field in with structured cores, and the dynamics of these choices ripple out to observable timescales in slow ways. The James Webb Space Telescope, while not aimed at neutron star interiors directly, can read the chemistry of kilonova ejecta in the infrared, extending the reach of merger forensics into bands where heavy elements paint strong lines. These data join the gravitational and X-ray constraints to tighten the box around allowed interiors. The pattern that emerges is not a single announcement but a braided argument. Heavy stars insist on stiffness somewhere. Tidal deformability argues against stiffness everywhere. Cooling and transient behavior give mixed hints that can be reconciled if superfluid gaps modulate familiar neutrino channels, while a deeper phase opens or closes brief taps. Pulsar timing of binaries adds the mass scale needed to anchor the whole plot. Each cycle of observation and modelling raises the question, anew do quarks march freely in the heart of some neutron stars? The honest answer remains that the doors are partly open. The corridors allowed by present data are narrow enough that a modest improvement in radius measurement or a single heavier star or a clearer post-merger ring could force a decision. Until then, the approach is to layer evidence, weigh more stars, time more binaries, catch more mergers and map more hotspots. The allure is strong because the prize is not only an account of one class of stars but a chart of how matter behaves when its usual boundaries dissolve. If quark matter lives in the core, the star becomes a natural collider that holds the state steady for as long as it survives, and by reading its gravity, light and heat astronomy transforms distant clocks into laboratories for the most fundamental questions about what holds the fabric of matter together when almost nothing is allowed to move. Binary dances begin when two neutron stars born in separate supernovae or forged as siblings in a single cluster, find themselves bound by gravity and circle one another for millions to billions of years, while frictionless space slowly saps their energy through gravitational waves and the long spiral inward converts orbital motion into heat light and a final symphony recorded across the spectrum. Long before the last minutes, the pair already shapes its neighbourhood. Tides lift bulges on each star that lag the orbit, and transfer angular momentum and magnetic interactions between magnetospheres flicker in high-energy light. When one star is a pulsar, timing catches the relativistic signatures of the close partnership. The Shapiro delay bends radio pulses that graze the companion's gravity field, mapping inclinations and masses. Periastron advances under general relativity, and orbital decay matches the energy loss expected from gravitational radiation. A famous double pulsar system shows both clocks in the same dance, and their measured losses agree with theory to exquisite precision, proving that the final plunge is inevitable, even if patience is required. As the orbit tightens and the stars approach the last stretch where minutes remain, the laser interferometer, Gravitational Wave Observatory Virgo and Cagra become the ears for the galaxy, and the frequency of the waves climbs as the radiators spiral faster. The signal is a chirp that sweeps upward in pitch and power, and the detailed phasing encodes the masses of the stars and a property called tidal deformability that describes how easily their shapes are pulled from spheres. A softer interior yields more stretch and a larger phase shift. A stiffer interior stays more round and refuses to bend. In the year 2017, a signal arrived that announced the coalescence of two neutron stars in a distant galaxy, and telescopes across Earth and in orbit pivoted to listen and watch. Within hours, the Fermi Gamma Ray Space Telescope and other monitors caught a short burst of gamma rays, softer than some but unmistakable in timing and association, proving that at least some short bursts come from neutron star mergers. Optical and near-infrared eyes saw a kilonova flare that brightened and then reddened over days, as radioactive elements forged in the ejector decayed and heated the debris, and the color evolution revealed two components: a fast blue surge from matter with few lanthanides, and a slower red glow from neutron-rich layers where heavy elements were born. The European Southern Observatory catalogued spectra where blended features signaled the presence of unfamiliar mixes, and the James Webb Space Telescope later read infrared lines in other events that hinted at specific species among the heavy elements. Radio and X-ray afterglows rose more slowly as a jet ploughed into the circumstellar medium and shocked it with the Very Large Array and the Atacama Large Millimeter Array, tracking the rise, the peak, and the fade. The pattern suggested a jet seen off its sharp axis filtered through a cocoon of slower material, and the shape of the light curve tied geometry to energy. This one event became a template. The masses derived from the gravitational wave chirp replied to the question of how heavy the stars were. The time profile of the gamma rays spoke to whether a jet could thread a cluttered environment. The Kilonova colors weighed the balance of ejection channels, and the late afterglow said how cleanly the jet escaped. In subsequent years, additional mergers have refined the story and introduced puzzles. Some events show a brighter blue component than models expected, implying that winds from the merger remnant or from an accretion disk were processed through intense neutrino radiation that raised the electron fraction and suppressed the formation of the heaviest lanthanides. Others skew red and slow, implying that tidal tails ripped out very neutron-rich matter in the instant of contact. The outcome depends intimately on the equation of state. A stiffer core survives compression and resists early collapse, allowing a hot differentially rotating remnant to live for many milliseconds to perhaps seconds. During that pause, neutrino radiation from the remnant can alter the composition of winds and shift the kilonova toward blue. A softer core collapses promptly into a black hole and leaves only the dynamical ejector and a thin disk behind tilting the kilonova toward red and dim. The Laser Interferometer, Gravitational Wave Observatory and its partners translate the phasing into tidal deformabilities that push theories towards specific stiffness profiles, and the kilonova colours then check whether the thermodynamics of the remnant align with those stiffness guesses. The synergy turns one violent hour into a diagnostic suite. Not all partners are the same. Some pairs join a neutron star with a black hole, and there the question is whether the star is torn outside the horizon or swallowed whole. If the black hole is heavy and non-spinning, the star disappears with little light. If the hole is lighter, or spins rapidly with a favourable alignment, tides can shred the neutron star on approach, throwing out a fan of debris that glows as a kilonova and feeding a disk that may launch a jet. The absence or presence of an optical counterpart thus marks where in parameter space the system fell, and the gravitational wave signal adds the masses and the spin to complete the picture. By stacking many events, observers hope to map the mixing ratio of neutron-star pairs to neutron-star and black hole pairs, and to watch how that ratio shifts with cosmic time, which in turn reflects how different stellar populations and their metallicities influenced binary evolution. The path to merger begins long before gravity waves. Binary evolution weaves through mass transfer common envelopes and supernova kicks. When the first star explodes, the kick can disrupt the pair or tighten it depending on direction and size. When the second star explodes, the new kick must again leave the pair bound. The distribution of eccentricities and separations in double neutron star binaries observed in radio transfers back into that origin story, and the chemistry of host galaxies gathered by survey telescopes tells how progenitors lived and died. The laser interferometer. Gravitational Wave Observatory has already placed constraints on how often mergers occur, and those rates mixed with models of chemical evolution suggest that kilonovae contribute a significant fraction of the galaxy's heavy elements, though not necessarily all. The riddle of where the heaviest nuclei originate now has at least one strong answer, and the patterns of abundance in ancient stars measured by high-resolution spectroscopy with the Very Large Telescope and sister facilities serve as fossil records to test the proposition. There are surprises in the aftermath. In some mergers, the engine behind the light may continue for months, as if a long-lived neutron star remnant pumped energy into the debris through magnetic winds. In others, the quick collapse shut off that injection, and the light faded on a simpler timetable. Polarization measurements hint at a symmetry in some kilonovae, aligning with the idea of a structured jet and a cocoon. Late-time radio reveals persistent sources that could be bubbles blown by continuing outflows, while X-rays sometimes brighten anew as shocks run into denser knots. Each deviation nudges models. The promise of standard sirens also appears because a gravitational wave chirp measures distance without relying on a chain of calibrations, and if a redshift can be read from the host galaxy, the expansion rate of the universe emerges. The first binary neutron star event offered the initial test with broad uncertainties, and subsequent events will tighten that line, adding yet another reason to chase counterparts quickly. Instruments coordinate in global networks that can pivot within minutes. Wide-field optical surveys sweep error regions for new points of light. Radio arrays comb for rising afterglows. The Neutron Star Interior Composition Explorer and the X-ray Multi-Mirror Mission Newton stand ready to catch early X-rays if a jet tilts our way. The James Webb Space Telescope turns its infrared eyes to later days when heavy elements write their broad blended features. Each instrument adds a brushstroke to a fast-evolving portrait, and the cadence of observation becomes as important as the sensitivity because the colours change with the chemistry and the geometry. The binary dance therefore acts as a unifier. It ties general relativity to nuclear physics, gamma-ray bursts to heavy element birth, and timing to chemistry. The chirp in gravitational waves reads the masses and the malleability of matter. The flash in gamma rays announces a jet. The glow in optical and infrared weighs ejector and its composition. The radio and X-ray afterglow map energy and geometry. From these pieces, astronomers infer whether the remnant lingered or died quickly, whether a jet escaped cleanly or fought through a cocoon, whether winds were bathed in neutrinos, and whether the stars themselves were soft or stiff at heart. With each new merger, the corridor of allowed interiors narrows, and the map of how the galaxy enriches itself gains new detail. Yet, as always, anomalies remain a kilonova that refuses to redden as fast as models predict a gamma ray, burst weaker than a jet should give a radio afterglow that rises too late. These oddities are the wedges that open the door to refinements, and to the possibility that mergers host more than one engine, perhaps including magnetar remnants that endure for a time and beam fresh energy into the debris. The dance is violent but instructive, and in the rhythm of in-spiral contact and collapse, the universe reveals how gravity negotiates with matter when both are pushed to their limits. Measuring the unmeasurable begins with a vow to let nature set the rulers, because a neutron star refuses any direct probe and offers instead a handful of signals that must be turned into size, weight, temperature, and stiffness by patient inference. Mass is the most mature of these measures. When a neutron star belongs to a tight binary, the dance itself reveals the weight of both partners. The peruastron of an eccentric orbit advances by a measurable angle, each cycle under general relativity and timing with Parkes Greenbank, the 500-meter aperture spherical telescope, and the legacy archives of the Arecibo Observatory pins that advance so precisely that the total mass can be read from the rate. When the companion aligns so that radio pulses graze its gravity field, the Shapiro delay adds a second ruler light takes longer to pass near mass, and the shape of that delay gives the inclination and the companion's weight, which combined with the total yields the pulsar's mass. Double neutron star systems add a third signature in orbital decay, the inexorable shrinking consistent with energy loss to gravitational waves, and the rate of that shrinkage closes the loop by confirming that gravity behaves as expected in a realm far from the solar system. With mass in hand, radius becomes the prize because the pair together sketch the inner grammar of matter. The neutron star interior composition explorer perched on the International Space Station watches X-ray pulses carve the sky as hot spots rotate into and out of view, and by modelling how light bends around a compact star, how beaming shapes the crest of a pulse, and how energy-dependent delays shift phase by a hair, the instrument infers the star's compactness, the combination of mass and radius hidden in the curve. To separate the two, one can use a pulsar already weighed by timing, or one can fit mass and radius simultaneously by letting the pulse waveform fold through gravity's lens, a method that rewards clean geometry and long stable datasets. The X-ray multi-mirror mission, Newton and the Chandra X-ray Observatory, add thermal spectra of cooling stars and of hotspots on accreting millisecond pulsars, while new X-ray polarimeters test whether light leaves the surface with a polarization pattern that encodes the direction of magnetic fields and the angle of emission. Polarization also samples a subtle twist imposed by vacuum birefringence near the surface of magnetars. A quantum imprint that once measured can clarify how the atmosphere and the field shape the beam. In bursts from accreting neutron stars, photospheric radius expansion can occur when the surface briefly exceeds the local Eddington limit and lifts the atmosphere. If distance is known, the peak flux and the cooling tail together bound the radius, although uncertainties in composition and geometry keep the answer provisional. In quiescent low-mass X-ray binaries, where a star rests between episodes of accretion, the soft thermal glow of the surface seen through a known column of interstellar gas can pin down the radius if the atmosphere is understood. Each of these methods is a filter through which reality must pass, and each flow of inference keeps a ledger of assumptions so that the sum can be trusted. Gravitational waves provide a different mirror: the laser interferometer, gravitational wave observatory. Virgo and Cagra read the phasing of the chirp as two neutron stars approach merger. The tidal deformability, the ease with which each star stretches under the other's pull, leaves a small cumulative phase shift, and this number depends sensitively on how compressible the core is. By converting phase into deformability, and deformability into a permitted band of radius for a given mass, the waves draw corridors in which nuclear physics must walk. The post-merger signal, though more elusive, promises still more. If the remnant survives briefly as a hot differentially rotating star, its principal oscillation rings gravitational waves at a characteristic frequency that tracks the stiffness of matter at the highest densities. Catching that tone with future sensitivity would let the inner core speak directly, the electromagnetic partner to a merger. The kilonova offers other constraints by weighing the ejector and its composition through color and duration, but for measuring the star itself, the waves are the most direct path across distance. Cooling delivers a long baseline test. Young neutron stars shed heat first by neutrinos from the core, and later by photons from the surface, and the slope of that fading temperature depends on which neutrino channels are active, on whether neutrons and protons have paired into superfluid and superconducting states, and on how the crust conducts heat. Chandra and the X-ray multi-mirror mission Newton follow the temperature of isolated stars over decades, while transient systems that heat during accretion and then cool in quiescence let observers watch entire thermal cycles over years. A star that cools unusually quickly could hint at a direct neutrino process opened by a particular composition, or even by a transition to quark matter. A slower slider suggests suppressed channels and large superfluid gaps. Strains on the crust carry a different hope. A star that bears a tiny mountain, even one only centimeters tall, radiates a continuous gravitational wave, while it rotates a whisper that targeted searches toward known fast rotators could in principle detect. A detection would measure the product of ellipticity and spin in a way that speaks to the crust's strength and to the core's ability to support deformation under magnetic and rotational stress. Even a firm upper limit feeds back by constraining how much heat such a mountain could make, how large interior fields might be without tearing their supports, and how efficient accretion is at building a permanent shape. Magnetism complicates and enriches every measurement. At the surface, the atmosphere's composition and the strength of the field alter opacities and can imprint broad features or depressions in X-ray spectra that, when modelled, narrow temperature and radius. Polarization across spin phase maps field geometry and tests models of magnetospheric scattering in magnetars, while mode switches in radio accompanied by torque changes proved that the global current system can reconfigure in minutes, a reminder that no measurement should be taken as static if the state has just flipped. Inside the presence of a proton superconductor corrals magnetic field into flux tubes whose motion and coupling to neutron superfluid vortices decide how quickly interior rotation follows the crust. That coupling in turn shapes glitch recovery curves so that a single timing record, when read with a trained eye, can finger the microphysics that also sets heat capacity and neutrino emission. The frontier techniques layer these clues rather than betting everything on one path. A pulsar with a precise mass from timing becomes a target for the neutron star interior composition explorer to extract radius. A kilonova with well-sampled colors narrows the range of remnant lifetimes that a gravitational wave fit allows. A cooling curve measured over a decade cross-checks the pairing strengths inferred from glitch behavior. Each pairing multiplies the leverage. Even the absence of expected lines or oscillations is news. If a magnetar flare lacks high-frequency ripples in its tail, the crust may be thicker or more strongly coupled than a popular model allowed. If a millisecond pulsar shows no sign of a continuous gravitational wave to a given limit, its crust may be smoother or its field more symmetric than theorists hoped. The method grows into a culture of uncertainty managed honestly, with Bayesian inference tying data and model into a map of likelihood that can be updated when a new event arrives. Selection effects are kept on the table. Pulsar surveys miss many beams, thermal fits can be biased by unknown atmospheres, and kilonova colors must be decoded through lines that overlap and broaden. Yet the map improves. The James Webb Space Telescope reaches the infrared lines that older facilities could not separate, and reads fresh letters in the Kilonova script. The Fermi Gamma Ray Space Telescope and the Neil Gehrels Swift Observatory extend burst catalogues to catch rare associations. Meerkat Green Bank Parks and the 500-meter aperture spherical telescope time arrays of millisecond pulsars, whose stability begins to test nanohertz gravitational waves from supermassive black hole binaries, proving that the clocks are steady enough to serve as metrology tools even as they whisper about their own interiors through tiny noise. Measuring the unmeasurable therefore becomes a choreography rather than a single step. Gravity provides mass and deformability. Light provides radius and temperature. Bursts and quakes provide elasticity and coupling. Timing provides torque and hidden exchanges. When results disagree, the disagreement is used as a lever to pry open hidden assumptions. When results agree, the corridor narrows and the equation of state loses another degree of freedom. The goal is not a final number, but a living set of constraints that evolve as stars age and as instruments refine. The mystery remains intact because each successful measurement poses a sharper question. If matter is this stiff here, what happens deeper? If a radius is this large at 1.5 solar masses, what will a star of 2 solar masses allow? If a merger remnant rings at this frequency, which phase of matter sang? In this pursuit, neutron stars teach the discipline of humility and persistence. They cannot be taken apart, they will not hold still, yet they yield one pulse and one photon at a time, and the measurement of what should not be measurable becomes the path by which their deepest layers join the conversation. Frontiers ahead unfold as a braid of new instruments, deeper catalogues and bolder questions, and each strand promises to tug at the layers of neutron stars from magnetosphere to core, while refusing the comfort of final answers. Radio skies will sharpen first. The square kilometre array begins to stitch together its vast collecting area, and with it comes sensitivity to beams that barely graze Earth, and to pulses that hide behind scattering fog near the galactic centre. The Canadian Hydrogen Intensity Mapping Experiment continues to broaden the census of fast radio bursts, some repeating, some one time, and each event becomes a test of whether magnetars alone can account for this restless population, or whether other engines share the stage. The 500-meter aperture, spherical telescope deepens the haul of faint distant pulsars, and hunts for the slow long-period emitters that bend rules about death lines and pair formation. Meerkat and the Parkes telescope push timing precision, and expand arrays of millisecond pulsars that serve as metronomes for nanohertz gravitational waves, so that the very act of listening for distant black hole pairs polishes the clocks needed to read superfluid whispers and magnetospheric weather. The next generation, Very Large Array, is designed to map pulsar wind nebulae with fidelity that turns wisps and jets into flowcharts measuring where reconnection converts field into heat and where shocks paint thin arcs that drift in months. Across the spectrum, polarimetry steps forward. The imaging X-ray, Polarimetry Explorer, opens a window into how light leaves magnetized atmospheres and how magnetospheric scattering shapes, angles through spin phase and future polarimeters, will harden those hints into maps in which vacuum birefringence near magnetars is not an exotic footnote, but a measured property of empty space under stress. The X-ray multi-mirror mission, Newton, and the Chandra X-ray Observatory continue to chronicle thermal evolution, crustal hotspots and nebular ripples, while the Neutron star Interior Composition Explorer refines radius posteriors one pulsar at a time, and together they provide the mass-radius pairs that equation of state models must thread. On the high-energy frontier, the Fermi Gamma Ray Space Telescope and successors keep watch for magnetar storms and for gamma-ray counterparts to mergers and ground-based arrays that catch the highest energy photons test, where the reconnection near the light cylinder can accelerate particles to staggering energies in minutes. Optical and infrared eyes grow stronger. The James Webb Space Telescope carries Kilonovae into late-time days where heavy elements write their broad signatures and surveys on the ground anchored by the Vera Sea. Rubin Observatory will sweep wide fields each night to catch the fast blue and slow red evolution of transient debris. With those light curves, models will test how remnant lifetime neutrino baths and disk winds decide whether the spectrum tilts toward lanthanide rich crimson or toward a cleaner bluer glow. Future giants such as the Extremely Large Telescope and the 30-meter telescope will resolve faint shells, track proper motions of compact objects that were kicked at birth, and measure abundances in ancient stars whose atmospheres trapped the fingerprints of early heavy element factories. Gravitational waves do not stand still. The Laser Interferometer, Gravitational Wave Observatory and Virgo pursue upgrades that will extend reach and improve low-frequency sensitivity, while the Kagra detector deepens the network in Asia. Proposed observatories such as the Einstein Telescope and Cosmic Explorer promise to hear mergers from far deeper in cosmic time and to catch post-merger ringing with the clarity needed to turn oscillation frequencies into statements about the stiffness of matter within the innermost kilometres of a star. Space-based missions that might one day listen in lower frequency bands would also track the slow-in spiral of heavy systems and sharpen the timing of when a network should stare at the right patch of sky to find the flash that follows the chirp. In parallel, earthbound nuclear physics adds its own pressure. Heavy ion collisions at the relativistic heavy ion collider and the Large Hadron Collider study matter at high temperature and lower net density, while facilities that compress nuclei in other ways probe the symmetry energy and the pressure of neutron-rich matter parameters that feed directly into the outer core of a neutron star. This complementary march constrains what microphysics can be trusted when extrapolated upward to densities that only stars can supply. Theories stretch to meet the data. Global magnetohydrodynamic simulations that include pair creation resistivity and current sheets now run long enough to produce mode changes and torque steps in silico and kinetic simulations, resolve reconnection islands that may be the seats of giant radio pulses and rapid X-ray flares. Crustal evolution models that couple Hall drift plastic flow and ohmic diffusion now carry magnetic stress forward for thousands of years to predict when a magnetar should storm. Superfluid models grow to include turbulence entrainment and flux tube interactions so that a glitch time series can be inverted into a map of pinning strengths and coupling depths. Equation of state work folds in constraints from mass radius tidal deformability and cooling curves to trace whether a phase transition to deconfined quark matter can live in the center without breaking what the outer layers demand, and post-merger calculations predict how such a transition would bend the gravitational wave spectrum. The search space widens for outliers that would force revision. A neutron star heavier than any yet weighed would sharpen the upper bound on stiffness. A radius significantly smaller at a known mass would soften the core and support a transition. A magnetar flare with a clear spectrum of long-lived oscillations would enable astroseismology that pins crust thickness and core coupling. A persistent continuous gravitational wave from a known fast rotator would validate tiny mountains and set the crust's yield strength. A long-period radio pulsar that remains bright and stable would demand a new accounting of how pair cascades operate at slow spin. A merger with no gamma-ray burst but with an extremely blue kilonova would argue for a long-lived remnant that injected energy through magnetic winds rather than through a jet. With each of these possibilities, the emphasis falls on coordination. Arrays of telescopes now act as a single instrument stretched over continents and wavelengths, and alerts fly in seconds so that radio-optical X-ray and gamma-ray eyes can see the same change in the same hour. Timing archives grow richer as observatories pool data to watch daily and catch glitches and state changes that know nothing of time zones. The habit of sharing and of posing hypotheses before the event so that predictions are on record is becoming standard, and that habit will speed the sorting of which ideas hold when the sky delivers a surprise. Amid rising precision, neutron stars remain generous with mystery. Magnetospheres still switch modes without a simple trigger. Glitches still arrive as though a hidden calendar were being kept in the dark. Magnetars still unleash flares whose first spikes rise too fast for easy reconnection stories. Kilonova colors still defy a single recipe. The equation of state corridor is narrow yet still wide enough to hide a twist near the center. These refusals are the oxygen of the field. They ensure that new instruments will not only confirm but also contradict. They promise that even when mass and radius are pinned tighter, there will remain room for deeper questions about whether quarks roam freely at the highest pressure, about whether color superconductivity changes cooling and coupling, and about whether the most strongly magnetized stars break their crusts in patterns we can one day forecast. The horizon expands in both directions outward to survey more remnants across other galaxies, and backward to read the chemistry of older stars as a fossil record of how often mergers happened when the universe was young. In that expansion, neutron stars continue to perform their double role as engines and as laboratories, turning rotation and magnetism into light, while turning pressure into a message that flows through timing spectra and ripples in spacetime. The frontiers are ready, and each step toward them deepens the mystery rather than closes it, which is exactly how this story should proceed. Night gathers around the small, dense stars that haunt the galaxy, and their engines soften to a hush that still speaks. In the quiet, a pulsar's beam slides past like a breath taken, and let go, and timing lines stretch across years with the patience of distant tides. Nebular wisps drift in slow arcs, fading as electrons spend what they were given at birth, and the shapes they leave behind remember the rings and jets that once pulsed harder. A magnetar cools by degrees, its twisted field relaxing by tiny slips that no longer shake space, and the crust beneath settles into a new balance that will hold until it does not. Heat crosses an envelope tuned by its chemistry, and reaches the thin atmosphere where it folds into light, that instruments catch and turn into numbers that mean size and weight and stiffness. Inside the darkness of each star vortices breathe their own rhythm, while flux tubes slide by almost imperceptibly, and the difference between motion and stillness is only the page on which observers choose to write. Far away, two remnants complete their long descent and merge in a flash that for one night acts like a lantern for the universe, laying colour on the sky that carries the signatures of heavy elements made in the rush. The afterglow lingers as a smudge that remembers speed and direction, then dims into the background where other stories wait. Across all of this, instruments keep watch without hurry. Radio dishes hold their stare, X-ray mirrors count and count again. Interferometers listen for the slow tide of gravity itself, and each detection folds into a map whose edges recede as it grows. The mystery does not shrink. It clarifies. Neutron stars remain what they have been throughout this night. Clocks and furnaces, storms and laboratories, the densest stable matter arranged by gravity into a form that will not let go. Their pulses recede into the dark, but the path they trace stays bright enough to follow tomorrow.